Our next unit here is going to be on solutions, and in our first lesson, that unit is going to be Solutions 1. In this unit, we're going to look at a few different things. We're going to talk about the properties of water, why water acts the way it does, and why it's such a unique substance. We'll talk about polar versus nonpolar substances, and what polarity is. We'll talk about electrolytes, and we'll talk about different types of mixtures. 3 different types that are going to be the main things we're going to look at here in this unit. First thing, properties of water. Water is, of course, as we are all quite familiar with, H2O. And so H2O, we have 2 hydrogen atoms and then 1 oxygen atom in that molecule. They are typically oriented as you see in sort of the picture that we have sort of down here. Is that the oxygen atom is sort of, obviously, is the larger one of those guys. The 2 hydrogen atoms tend to attach all sort of on the same-ish side. And so they're at sort of an angle like this. It's 109.5 degrees is the angle between the 2. So it's just slightly over a right angle between them. The reason why that does this has to do with, if you remember way on back to our to where we talked about electron configurations, is the fact that the 2 extra spots, the last spots in oxygen's valence shell that are going to be filled, are in that 2p orbital. And remember that 2p has 3 different suborbitals. And so basically is each of those suborbitals at right angles to each other. You can think of one as like the x-axis, one at the y-axis, one at the z-axis. And so if 2 of them are empty, then it basically means you have 2 things that are basically close to right angles that are available for the hydrogens to share electrons with. And so as a result, they come out close to a right angle. They're not quite because of some repulsion due to the positives that are at the nuclei of the hydrogen, so they tend to push away from each other, and so it's slightly off of a center line here. But this is roughly what a water molecule is going to look like. It has sort of its oxygen atom that's right here, and it's got its 2 hydrogen atoms that are right here. Okay, and so this is our shape. You can sort of see the same sort of thing over on this side. We have our big oxygen and our 2 hydrogens on the sides here. So let's take a look at what this means for water. If you look at the oxygen atom in this case is, once it has bonded with the hydrogens, now has a full second energy level. Its valence shell is completely full because it has, if you count them over here, it has, 1, 2, 3, 4, 5, 6, 7, 8 electrons right along in there. But if you look at that, you see that on sort of what's now our top side of the oxygen here is that we have all these electrons right up here. There are 8 protons are sort of in the middle here, 8 protons and 8 neutrons, roughly, for an average, oxygen 16 isotope. So we've got a lot of negatives up near the top. The positive is sort of surrounded by negatives, but we have sort of a negative top side here. Let's look at the hydrogens, though. The hydrogens have 1 proton sitting right in the nucleus here. The electrons for each of the hydrogens are sort of on the inside because the one that it shares, remember, actually only one of these is actually the hydrogen's electron. The other one is basically the one it's sharing with the oxygen. The electrons for the hydrogen are generally always going to be towards that positive nucleus on the oxygen atom. They're going to be attracted into that positive nucleus there. And so as a result, the electrons, the negatives of the hydrogens, tend to be on the inside of the water molecule, which means that the bottom part of the molecule, this part right down here, is mostly going to see these positives that show up from the nuclei here. As a result, we end up with the bottom part, that is the hydrogen part of the water molecule, is going to be positive. And so overall, looking at this, over on our right side one here, you can sort of see that the oxygen atom, because of these electrons right in here, is going to be negative on one side, and it's going to be positive on the other due to the hydrogens and their nuclei that are sort of sitting out here. The term for this is called a polar molecule. It has 2 poles. It has a negative pole and it has a positive pole down here. And what that means is that if I have a bunch of water molecules that are all together, mixed in together, is that what they're going to do is they're going to try to line up. Is that the positive sides of a water molecule is going to be attracted to the negative side of another water molecule, and vice versa. And this is sort of what we end up getting here. This structure of water as a polar molecule is the reason why, or one of the reasons why, water is so special. It's why it's necessary for life. Why, really, it's one of those things that is it's almost unique in chemistry of the things it does, and it's almost entirely due to the fact that it is this polar molecule. Also, it's due a little bit of being a very small molecule, but the polar part of it is the most important part. So let's take a look and see what that means. This polarity that causes attractions between these water molecules due to the positive and negative poles is called hydrogen bonding. And so hydrogen bonding is sort of our term that deals with this. Basically, it's because of the attractive forces between between the protons and the hydrogens and between the negative electrons that are on the outsides of the oxygens. And so in sort of this diagram that we have over here on the left side, you can sort of see is that it sort of uses dotted lines. So we have our water molecule here, and so we have the hydrogens that are, right here. We have the oxygen that's right there, and we can see they're bonded together. That's what those are showing right there. But we also see we have these little dotted lines that connect them right in here. What that's showing is that the positive hydrogens are attracting the negative bottom sides of the oxygens. Same thing here. The negative side of the oxygen attracts the positive side of the hydrogen here. So as you can sort of see, they all connect together like this. This hydrogen bonding is a form of attraction between water molecules. It is not a particularly strong form of attraction, but it's strong enough to be noticed. Let's put it that way. It's still very easy to move water molecules apart from each other, but they do have some attraction. And this hydrogen bonding, this attraction between them that we call hydrogen bonding, leads to water being effectively very sticky. Our word for this is actually called it being wet. That property, if you stick your finger in water and the water sort of sticks to your finger, that is largely due to hydrogen bonding. It also is the reason why if you take some water and fling it on a table, you'll see it beads up. The reason why it does that, instead of spreading out, if you take alcohol, pure alcohol, spread on a table, it'll spread out completely. But water sort of beads up because these molecules are all sort of attracted to each other. This hydrogen bonding pulls them together. They want to be that the negative sides on ones are attracted to the positive sides on the other, and vice versa. And so they all pull together, and so you end up with a case where they want to pull together, and you end up getting these little beads up of things here. It also is the reason why water has such a high surface tension. You can even get to the point where if you take like a staple, you can actually put a staple on the surface of water and it'll sort of float. I air quoted that. You can't see it. It isn't really floating because it's more dense than water. But what basically is happening is those intermolecular forces, that hydrogen bonding between the water molecules is strong enough that it can support the full weight of that paperclip, or that staple. So also if you ever see like water skimmers, the little bugs that go off across the surface of the water, that's basically what they're doing, is that they have a small enough force that they're putting down on the water, or small enough pressure actually, that they don't interfere with the hydrogen bonding, and the hydrogen bonding is able to keep the water molecules close enough that it holds them up. So that's one type of thing this polarity does. This hydrogen bonding, due to the fact that water's polar, leads to the property of water. Another one, as it sort of says down below, it said this hydrogen bonding results in a low vapor pressure. So we talk about water when we talked about vapor pressure, that your water molecules in a liquid occasionally will get enough energy to be able to jump out and escape, turn into a vapor. But due to this hydrogen bonding, the molecules are sort of attracted to each other, and so it makes it harder for them to escape than would another substance that's the same size molecule as water but isn't polar. Those molecules don't have as much hydrogen bonding or even any hydrogen bonding, and so they escape very quickly. It's easy for them to do it, and they would have a higher vapor pressure. Water, though, because of the hydrogen bonding, has a low vapor pressure because not very many can escape. It also has relatively high melting and boiling points compared with other things that are the same size as water, same size molecule. The reason why, if you think about this, why would it have a high boiling point? Well, if there are stronger forces between the water molecules due to the hydrogen bonding, it's going to take more energy to get them to basically turn into a gas. Same thing is true if it's a solid. If it's a solid and it's got all these bonds between molecules, then it's going to take more energy to be able to break those bonds because they're so attracted due to this hydrogen bonding. And then lastly, it also means they have a high specific and latent heat. And so basically, once again, is that it takes more energy to be able to get the molecules to break apart, or more energy it gets them to basically to change phase, because the bonding sort of makes it harder, more work you have to do in order to break that hydrogen bonding. It is possible, though, to break the hydrogen bonding in ways other than just adding more energy to it. There is a way of doing it where you actually insert a new substance in. This is called a surfactant. We sort of have the name down here, surfactants, or sometimes called wetting agents. They interfere with hydrogen bonding. Usually, what they basically do is there's substances that will break up, and the substances will basically go in and they will sort of get in between your hydrogen bonds here, they effectively will either attract to the negative sides. They'll have like one negative side or one positive side and one neutral side. And so the positive side will go in and will attract to, say, an oxygen molecule down here. And the other side's roughly neutral. And so then you've basically sort of cut off that bonding site, that it won't want a hydrogen bond to that one anymore. And so these surfactants basically interfere with hydrogen bonding. And so as a result, basically make the water's connections worse, effectively. It makes it where they don't have as high hydrogen bonding. And if you do that, you're basically going to undo all this stuff that we talked about on this section right here. A common thing that does this is actually soap. Soap will interfere with hydrogen bonding. If you have one of those little water skimmers that's going around here, if you have him like in a little fish, if you have like a fish tank, don't do this with fish, obviously. If you were to basically put soap in there, make it soapy water, he wouldn't be able to stay up on the surface. The soap would interfere with the hydrogen bonding, which would lower the surface tension of the water, and he'd basically fall in. He wouldn't be able to skim across the surface like he does normally. Or similarly, it wouldn't hold up that staple that we were talking about before. So these surfactants are wetting agents that keep it from beating up. It's one of the reasons why we do add soap to clothing as well. Or detergent is actually more common in this case, whenever you're washing things, is that those surfactants interfere with the hydrogen bonding so that the water doesn't beat up on your clothing. It soaks through and the soap can work its way through. And so this is sort of where we get from this right here. So let's keep on going with what we've got here. We talked about this a little before. We said, when we were talking about water, we said that we were comparing with always molecules of the same size. The reason why is this, is that larger molecules typically have higher intermolecular forces, higher forces of intermolecular attraction than smaller molecules do. The reason why are basically the more atoms that you have in a molecule is the better the chance that, say, that all your electrons are going to be on one part just by chance. Remember, your electrons in the electron cloud are sort of not in any one place. They're sort of all around. There's a probability. But sometimes that probability will end up being so that there are more electrons on one side than the other, and that would make that part of the molecule negative. Or if they're on the complete opposite side, it would leave that bare nucleus there, which would give you more of a positive side. And so the larger the molecule is, the better the chances of that type of thing happening. And having these very, very brief forces that go in between molecules here. So larger molecules have higher intermolecular attractions between each other than smaller molecules do. Smaller molecules typically do their own thing. So thus, the smaller the molecule, the more likely to be a gas at a certain temperature. Because if you have a smaller molecule, they don't attract each other as well, and so it's easier for them to be able to escape and go free, and basically escape into a gas. A larger molecule has these higher intermolecular forces. They attract each other more due to these very quick transient forces between each other. And so these forces hold them together, and so it takes more energy to be able to turn them into a gas. Polar substances, like water, however, are less likely to be a gas at a certain temperature than molecules with similar size. Why? Because of the hydrogen bonding. All the forces between the positives and negative sides on your water molecules holds them together. This is actually very critical to the fact that life will exist on Earth. If water was not polar, then based on its molecule size, it should be a gas at the temperatures we live at. And so as a result, we would have, if water wasn't polar, we would have no liquid water on the surface of the Earth, no solid water on the surface of the Earth. It would just be as a water vapor. So no oceans, no liquid water. All the water that's inside of you, that's inside pretty much every living thing, would not be able to exist at this temperature. You'd have to cool it way, way much cooler. And if you cooled it way much cooler, then the other processes that life needs to survive, at least life that we've discovered, would not work properly. And so it is this polar... The part of water that makes it polar is actually very critical to the fact that we can survive. And so those intermolecular forces make it harder to turn into a gas, and so it keeps it as a liquid or as a solid at much higher temperatures than we'd expect otherwise. So, that being said, polar versus nonpolar substances, there is a general rule if you're trying to dissolve a polar versus a nonpolar substance, and that's that polar substances most effectively dissolve other polar substances, and nonpolar substances most effectively dissolve nonpolar substances. Usually this is expressed in the term like dissolves like. And so when we're saying that, all we're saying is this, is that if I have a polar substance, and I want to dissolve it, I want to use a polar solvent, something to go in and take it in that way. If I have a nonpolar substance, I want to use a nonpolar solvent. Classic example of this is this. If you have gasoline on your hands. Gasoline is generally a nonpolar substance. If you try to take gasoline and just try to wash it off in water, it doesn't do a very good job. because water's polar, gasoline's nonpolar, and so it won't dissolve it away. You typically have to use soap. Soap typically has a polar end and a nonpolar end, so it'll attract both of them. Or if you get tar on your hands, tar is also nonpolar. And so if you try to wash tar off in water, it doesn't work very well. But if you try to wash tar off in gasoline, the gasoline will take the tar right off. I wouldn't suggest taking a bath in it because that's sort of all sorts of deadly fumes from it. But if you have some tar that won't come off your hand, using gasoline or using alcohol, also nonpolar, will work really, really well because polar substances dissolve other polar substances. Nonpolar substances tend to dissolve nonpolar substances. Like dissolves like. So, whoops, didn't mean to do that. Continuing here. Polar substances will also dissolve ionic substances. Remember that we talk about ionic substances, we're talking about ions, these compounds that whenever you put them into water will split up into their native ions, like mostly, commonly this is salt, NaCl. You have sodium and chlorine. When you put them in water, the sodium basically has its electron stolen by the chlorine. The chlorine ion now, the negative chlorine ion goes off its own way. The sodium ion goes off its own way. They don't stick together anymore. This is an ionic substance. If you take an ionic substance and dissolve it, which would typically be in something that's a polar substance, a polar solvent, the solvation of ionic compounds results in unbound ions that can move throughout the solution. So your positive ions can float through the solution, your negative ions can float through the solution, and they don't have to meet each other anymore. They just go off their own direction. Now, because of the fact that these positives and negatives can float wherever they want to within a substance, if I were to basically take a battery and hook it up to either side so that one side of the solution is negative and one side of the solution is positive, then all the positive ions would go towards the negative side. All the negative ions would go towards the positive side. We have a flow of charge. A flow of charge is called electricity. And so that substance would conduct electricity. So such solutions that can conduct electricity, because their ions are free to move around, are called electrolytes. That's the reason why that's where the electro comes from here. Electrolytes are basically substances that can conduct electricity. And they can conduct electricity because they have ionic substances dissolved in them. When you hear about like like sports drinks, like Gatorade, things like that, they talk about them having electrolytes. They're referring to the fact that basically that they have salts in them. Salts, we said, break up into positive and negative ions. Your body needs those extra salts whenever basically you're working out, or they need to replenish them. And so basically these sports drinks replace those salts, and because of the fact that they can conduct electricity because they have those ions in them, they're called electrolytes. So the electrolyte part really has nothing to do with when you need sports drinks. You don't really need to conduct electricity. It's just the salt you need also does conduct electricity, and so they call them electrolytes, or replacing those electrolytes. Now, if you have the substance that you have dissolved, if it completely breaks into ions, it's simply called a strong electrolyte. If it only slightly breaks into ions, like some of the molecules break up into ions, some of them stick together, then that's just called a weak electrolyte. That's pretty straightforward. Pure water. If I take water and get everything out of it, it's completely pure. Sometimes this is called distilled or deionized, and that deionized is the key part here, has very few free ions. In fact, you did it perfectly, it would have no sort of alien free ions. And because it has no free ions in it, that means it conducts electricity very, very poorly. This is something that sort of most people tend to assume. You always hear about, when lightning strikes, you want to go away from water. Water is actually a really, really bad conductor of electricity. Pure water is. It's only when you dissolve stuff in it that it becomes pretty good. In fact, one of the reasons why you don't want to be in water whenever lightning strikes is because of all the things around, the water doesn't conduct electricity very well because it's generally pure water. So you're not in an ocean, if you're in like a freshwater lake, but you are full of salt. You've got salt and water. You conduct electricity pretty well. You're the best conductor around, and so lightning would be more likely to strike you if you're in water than it would otherwise. Water is a better conductor of electricity than air is. And so, if you have a choice of being in water versus being in air, you would probably be better in air. But in general, water is a really bad conductor of electricity unless it has these dissolved ions in it that can move around and then conduct electricity through it. So that's basically what an electrolyte is, and that's how those guys work. Continuing here. Mixtures, sort of our last topic here. Anytime you take particles of one substance and spread them out inside another substance, and this process is something called dispersion. is that there are three types of mixtures that you can get out of this. The first one is solutions, the second one is suspensions, and the third one are colloids. So here's what we have here. A solution. Solutions are defined this way. In a solution, the particle that's mixed in, the particle size in a solution is less than 1 nanometer. So it's really tiny, less than 1/1000th of a meter. Really tiny here. And in a solution, the mixture is homogeneous. And so in this case, the root homo here means same, and so basically it means it is spread out the same throughout the whole mixture. So that you wouldn't have, if you have a salt water solution, is that the salt ions are mixed out sort of entirely through the whole thing. There aren't more of them at the bottom than there are at the top. They are uniform throughout the whole substance. They are homogeneous, and the particles are very, very small, less than 1 nanometer. On the other hand, in a suspension, the particle size is greater than 100 nanometers. And so still pretty small, but at least 100 times, usually more than that, larger than the particles in a solution. And these particles in a suspension are large enough that they settle out. Is that they basically have enough mass that if you mix up a suspension, then they'll all sort of fall their way out. They'll work their way to the bottom, and you'll end up with stuff at the bottom of your container. Whenever they fall out, this is called a precipitate. If you do have one of these here, if you're creating one as you're going here, an example of this would be take river water. If you take river water when it's been flooding and it's really sort of dirty water, you take it up and it's sort of brown water, but if you let that sit aside for a little while, eventually all the stuff that's in it will settle to the bottom. The reason why is because that's a suspension. If you, on the other hand, to go down to the ocean and take salt water, set it aside, it's pretty much always going to be salty for the whole thing. The salt will not settle to the bottom. So if it doesn't settle, then it's generally going to be a solution of these two guys because the particles are too small. If it does settle, it's typically going to be a suspension. So suspensions, the particle sizes are greater than 100 nanometers, and the mixture is heterogeneous. Hetero means different because of the fact that basically the particles will eventually settle out. But these are only two of the types of mixtures that we talked about. Let's see if I can get my guy to go on here, page 10. Okay, but actually before we get to our third one here, particles in solutions are generally too small to be mechanically filtered. And so, but particles in suspensions can be filtered out. They're big enough for this to work. So if you basically take salt water and put it through filter paper and try to filter it out, you could never get the salt out. You cannot filter out particles in a solution. They're too small. In suspensions, though, you can filter them out. If you take that river water and put it through a coffee filter, you can filter out most all the bad stuff that's in there. That's why you have like water filters that you may have for drinking water. Basically, is that if it's a suspension in it, it's got those other particles, that'll pull those out no trouble. Now, one way to tell whether you've got a solution or a suspension, outside of waiting for it to settle out, is to use something called the Tyndall Effect, and that's what we have a picture of right here. So the large size of the particles in suspension cause light passing through to be scattered, and this is called the Tyndall Effect. You can sort of see the picture that we have here. We have a green laser that's being basically shot through a suspension, and because of the fact it's shot through a suspension, you can see the beam. Basically what's happening here, and so if I can find a pen that'll work this way, is the light comes out of the laser. Whenever it basically hits these particles, they're large enough to cause the light to sort of jump off in some other direction, and so it bounces off. It doesn't just go straight through, and so any light that's coming out here bounces off in some direction. And so including what'll happen is it'll bounce off and it'll come straight towards your eye. And so that way you can see the beam going through the liquid here. As opposed to, and I sort of covered it up, so let's bring this back out here. As opposed to sort of out in this region where it's going through air. You can't see the laser beam there. The reason why is because there aren't large particles in the air to scatter the light. You can only see it when it's going through the suspension where the particles are large enough to scatter the light and send it to your eye where you can see that beam. This is also, this Tyndall Effect explains why sometimes, if you go outside at certain times, you can see sunbeams. Is that what you're seeing here is a suspension in the air. There are dust particles in the air that are large enough to reflect the sunlight and to scatter it out so you can see it with your eyes. And so this is the Tyndall Effect. Anytime you can see a beam of light going through something the way we can in this sort of diagram right here, that's your Tyndall Effect. It will not occur in solutions because the particles are too small. It will occur in suspensions because their particles are big enough for this to work. So solutions do not exhibit the Tyndall Effect. Suspensions do exhibit the Tyndall Effect. So continuing here. So in between solutions and suspensions are what we call colloids. We said before that that in a colloid, so the particle size is between 1 and 100 nanometers. We said less than 1 nanometer and it's a solution. Over 100 nanometers and it's a suspension. And so this is a colloid, has those particles in between those two. The mixture in a colloid is homogeneous. The particles are spread out evenly throughout the substance. The particles generally can't be filtered. You can't get them out that way. In a colloid, they're too small to be filtered. So far, everything's been exactly the same way as a solution. A solution, the particles are small, they're homogeneous, they can't be filtered. So what makes this different than a solution? Well, one thing is that if you look at the Tyndall effect, it's only very slight, which would mean which is different than a solution here. In a solution, of course, remember that the particles are too small to scatter light, and so it won't occur. You shine a laser through salt water, you're not going to see the beam. Particles are simply too small to scatter the light. So the fact we have a slight Tyndall effect tells us that we have something a little bit different going on. And it turns out that the reason why that we have to have the separate colloid as a category here is that the particles in a colloid technically should be too heavy to be homogeneous. They should filter out. They should settle out. They should be too heavy for that. But basically what happens is that in a colloid, the particles tend to all develop the same charge. And so you'll all have all positive charged particles or all negative charged particles. And so if I have my particles down here in my colloid that are dissolved into this guy, they all positive, say. If another one comes down here, it's also positive. What's it going to do? It's going to be repelled by the one that's below it. That should be positive. It looks like a negative down there. And so as a result, the next one that comes down that's also positive is going to be repelled upward. They all sort of push on each other and push each other away. And so as a result, they spread themselves out throughout the whole solution. And you end up with a homogeneous solution, or not homogeneous mixture. Sorry, not a solution. This is a colloid. A homogeneous mixture that we get out of it here. And so this charged particle aspect of this, the fact that the particles in a colloid are charged, means that they tend to repel each other. In a suspension, they oftentimes are also charged, but they're simply so heavy that they overcome that charge and settle out anyway. And so this is basically what we have for a colloid. Now, different types of colloids that we're going to run into. If I can get to it here. If it'll let me get to it. All right, so one type of colloid where you have one liquid that's dispersed in another liquid is called an emulsion. Classic example, milk. In milk, you have basically, well, if you know your milk, you talk about having, it has sort of cream to it, and it has sort of the liquidy part, the whey. Technical term, I believe it is. Basically, you have two liquids that normally will separate. But in milk, you've got these two liquids that would normally separate are all mixed together. It's called an emulsion. Typically, if you have liquids that normally will not mix, you have to add what's called an emulsifying agent. Soap is another example of this, that can be added to break the liquids into small particles that then can be spread out into this colloid. Typically, all emulsions are colloids. Typically, things like milk. Milk is an example of a colloid here. And so basically, it breaks up what you've got into small little pieces. These small little pockets of liquid can then basically mix up through the whole thing. And so that's what happens in milk. Other types of colloids. So an emulsion is a liquid mixed into other liquid. If you have a solid that is mixed into a gas, that's called smoke. Because you have little solid pieces, ash, that are mixed in with everything else. If you have a solid that's dispersed in a liquid, that's called a gel, like Jell-O. You basically have small little pieces of gelatin that are evenly spread out throughout a liquid, which is why the Jell-O has sort of this liquidy solid sort of thing. It's like it's halfway in between. Reason why is because it's basically got solid pieces dissolved in a liquid. So it has some properties like a solid, some properties like a liquid. If you have a liquid dispersed into a gas, that's a fog. You have little water molecules, well, not water molecules, but little, because actually in a fog, that's the difference between, like, say, when you see a fog of water vapor and just talking about water vapor. Water vapor you can't see. There's water vapor in the air surrounding you right now. You don't see it out there. The molecules are far, far too small. They're quite technically sort of in solution in the air. In fog, though, you can see it. And if you shine a flashlight through fog, you can see the beam. It's a Tyndall effect. The reason why is because that basically you have these larger water droplets. They're not big enough to fall out, because then it'd be a suspension. But they're small enough to be held out here, and they spread out throughout it sort of evenly. You get this homogeneous mixture. And so a liquid dispersed in a gas is called a fog when it's a colloid. If you take a gas and disperse it in a liquid, that's a foam. And so that's the term that we use sort of for that one right there, because you have the little gas pockets that are mixed up all throughout a liquid. And so you get something that, once again, is somewhat liquid-like, somewhat solid-like. We actually have gotten the point, is it's not, I haven't mentioned it up here, but there are what are called aerogels these days that basically are instead of being a solid that's dispersed in a gas, it's a gas dispersed in a solid. And for those, that's another type of colloid. Basically, you end up with something that has all the properties of a solid, but is incredibly, incredibly light. They've started making some pillows and other things like that and other pads out of them, because you basically have something that's extremely, extremely light, because it's mostly air, but it's dissolved into a solid, and so it has the strength properties of a solid, but has like the weight you would expect of a gas. But that's another example of a colloid. These are all examples of colloids we have here, and so that's basically what a colloid is.